Recording is in progress. Okay. Let's go. So 25 questions, each worth 5 points, and there's 25 extra credit points. So it means you can get 5 questions what's wrong, and as long as you get the extra credit right, you're good. So, yay. Okay. You are allowed your model kit, which I would recommend bringing, just in case. Huh? Okay. Because some of these problems might require it. Okay. Okay. Let's go. Let's do this instead. Let's make the speakers 100. Sorry, I'm just trying to make sure I can hear myself talk. Hello, hello, hello. Okay. So myself sounds kind of quiet. Let's try this for a little bit, at least. Which is one perspective, subjective structures best represents the Newman projection. So we need to know how to do Newman projections. So do you guys understand Newman projections? Zoomies, is there anyone who does not understand Newman projections?
I would enjoy a recap, please.
Who destroyed my computer? It's so quiet. No, 1 second. Mess. Okay. I connected here. Make sure this is going on. Sorry, 1 second. I'm trying to just go and check. Does not work. Why is it not connected to any devices? Just connect. Disconnect. I hate this. Now we go. No, computer audio. Okay. So you guys understand Newman projection? No, yes, maybe so.
No.
Okay, someone said no. So the way Newman projections work is imagine you are seeing the carbon structure like this. So that would be your first carbon. This would be your second carbon. So what you do is draw a circle. The circle represents carbon 2. And then you draw everything on the first carbon. Oh, this is kind of crazy. Okay. So I'll put that back on. I'm just hearing double audio makes me sound drunk. Okay. So you're gonna put everything you have on in the inner circle is gonna be carbon 1. So we have bromine, hydrogen, and alcohol. We then have H, SH, and chlorine. So if you look, they all have the same bonding order, right? They each have OH in the front carbon, correct? So you can't eliminate them based off of bonding order because they're all the correct bonding, right? What you have to do instead is you have to know that with Newman projections, anything off to the left side, so bromine and this 8SH thing right here, those are going to be dashes. H and Cl are going to be wedges because they're off to the right. That's just how Newman projections work. OH and H are going to be normal structures. Okay. Does that make sense to you guys?
Yes.
Okay.
Thank you.
Yes. Okay. So which one shows Br and SH in the Newman projection, or shows them as dashes?
Excuse me, I have a question. Did you say that the H and the OH are just a straight line?
Yes. They are a straight line. Because you can only have, if you have a dash, you have a wedge. You can't have both. You can have 2 dashes and 2 wedges. Each carbon can only have one or the other. What? You guys okay? Okay. Might have been better just having no one in the classroom. A, C, and E. Okay, A, C, and E. Cool. Then we gotta find one in which okay, so A, C, and E, that are correct. Those have BR and SH as the dashes. So what is wrong with C? All right. Is there anything wrong with it? Yes or no? What do you guys think? So the answer is A. So what's different between A and C?
It had to do with the hydrogen being in the front.
Well, technically, with this one, A is also a wedge too, right? So what's going on here? Yes, exactly. So the reason why A is the correct answer is even though this is going straight down, it has going straight down, right? So that means it has to be going straight down in the line angle form. So that one's technically, if you think you're looking at it, right? Technically, if you're looking at it, right? Here's your eyeball. The OH theoretically would be going down right there. It would be going up with C and it would be going up with E. So that's why they are wrong. All right. Also, E is just wrong in general because Cl is going to be on the second carbon, the back carbon, not the front carbon. So that should be on the second carbon, not the front carbon. That's why E is wrong. Make sense, Zoomies?
Yes.
That's why A is the right answer. Okay. Cool. Newman projections are heavily tested in your stuff, so please, please, please understand it. So, which of the following is a conformer or pentane? So, let's break this word down. Pen means what? How many? Good. Zoomies, and when I say something?
5.
5, correct. So pen is 5, and then A and E, what's that mean? Single, double, triple? Yes. Zoomies,
Single.
A and E, single, double, triple,
Single.
single. Good job, Jocelyn, thank you. So yes, A and E is single, so no double bonds. Okay. So going on here, we got to figure out what's going on. And remember, how Newman projections work, it's one carbon bonded to another carbon. So this first carbon is going to be all of these red dots, which would be this carbon. The circle represents a second carbon, which would be this blue carbon. Okay. So when you count carbons, you count 2 with Newman projections. So let's do that. That would be 1, 2, 3, right? 4. So A is 4 carbons in a row. Carbon chain of 4. We don't see that. Right? And then you have this. Those are all your carbon chains. That is not pentane, that is butane. A is wrong. That guy's connected, right? That guy's connected, that guy's connected. They're all connected to carbon 1, right? That is an example of propane. 1, 2, 3. You see that? Okay, so B is wrong. Okay. So that there is bonded to carbon, this one. And then this guy is bonded to the second carbon. So that is CH2, CH3, 1, 2, 3, 4, 5. Right? That is going to be C. Oh, never mind, my bad. That's actually D. I just showed you what D looks like. I misread it. Sorry. For C, I drew the circle so much. That's connected to the second one as well. So you'd have this. CH3, CH2. So you would have this structure. So 1, 2, 3, 4. You'd also have butane. That's incorrect. So draw the red one again. Draw the blue carbon. Right? Draw the methyl group. And then draw your C2CH3, which is right there. 1, 2, 3, 4, 5. So your answer is D. Does that make sense, Zoomies?
Yes.
Okay, cool. As long as someone says yes. Moving on, last chance. Okay. So 3. Which molecule represents a chair ring flip? Well, hopefully you guys know that this conformation right here is a ring or a chair conformation, right? And a chair conformation is just cyclo. 1, 2, 3, 4, 5, 6. Cyclohexane, yes. Wait for someone to say it. Someone to hear someone say it. So it basically is cyclohexane. How chair conformations work, we can either have molecules going up and down or left to right. If you guys have ever seen a globe before, like the ones on the like globes for planet Earth, the one that goes all the way around the globe horizontally is called the equator. So ones that go left to right on the chair conformation are equatorial. We call those E. Ones that go up and down are axial. So A. Okay. So let's look at this. This green guy right here, equatorial axial. He is axial. Good. There's 2 blue ones.
Equatorial.
Equatorial, good job. Cool. So during a ring flip, what occurs is the molecule literally will flip, right? So this end flips over, correct? And kind of flips, on its side, right? And what that occurs is all axial become equatorial, all equatorial become axial. They flip things. So let's look at this. So what is wrong with A? Well, the guy that was right there, which would be 1, 2, 3, he changed entire molecules. You don't break bonds with a ring flip. You only flip axial to equatorial. So A showed a bond breaking. Do you see that? 1, 2, 3. Kind of doesn't work too well, right? So it kind of shows a bond being broken. Does it make sense or no? No? You don't see bond being broken? Okay. Sorry. A is the wrong answer. A is not right. The reason being is a ring flip does not break bonds. It just switches axial equatorial. This guy right here is an ethyl group, correct? Right? And both ethyl groups now are, for A, are on the edges. He was not on the edge, he was one of the inner ones, right? So that guy and this guy switch places. You can't do that for a ring flip. You don't break bonds. So that's why A is wrong. A is a no-go. Okay. Same thing technically occurs with B. You also break the bond, right? The two edges one's a methyl group, one's an ethyl group, both become ethyl. B is wrong because it shows a breaking of bonds. Okay. Same thing with E. E shows a breakage of bonds. Same thing. So E is also wrong. So now we have C and D, right? This guy was equatorial, that guy was equatorial, that guy was axial. So he should become, the axial should become what? Equatorial. This guy should become axial. This guy should become axial, right? And we kind of see that with one of these. And that one is C. That making sense?
Wait, so the axial becomes equatorial?
Yes.
Which one in
There
C
is
is
an
it?
issue. If you do see it. This guy stays equatorial. There's a reason why. You guys ready?
Yes.
Heavy molecules can only ever be axial. Heavy molecules, because it's more stable. Oh, sorry, yes, my bad. My bad. Heavy molecules are equatorial. My bad. Reason being, there's less steric strain because molecules going up and down, electron clouds kind of interfere with each other. Molecules going equatorial back and that way do not. So there you go. So I see the answer.
How do you determine whether something's like heavy or not?
It's anything more than a hydrogen, really.
Okay, thank you.
It looks like a bonds breaks. I know. Oh. Yeah. No, they were both equatorial. This guy right here is coming off at an angle. That makes it equatorial. Going straight up and down is axial. Like for example, this guy right here might look like it's going up, but it's at an angle, makes it equatorial. It's stupid. I agree. That's how it's drawn. Okay. You okay? Okay. Number 4. Okay. Dihedral angle between two methyl groups is the most stable conformation for which is the hexane. Okay. Shown below. What angle would the method get? So to about dihedral angles means comparing two methyl groups, which we have here and here. What is the most stable chair conformation? What is the most stable chair conformation? Opposite substitute high cyclohexane. Right? So what this is trying to say is those two methyl groups are attached right to each other, right? The best way of looking at this is a Newman projection. Right? Okay. If we're looking at it like this, it would technically be like that. Okay. Let's draw it better. Since we're looking at it straight down, going off like this, going off like this, technically speaking. And then, oh, this is so weird. I hate Newman projections when you have to draw it correctly. And then that would be down here. And I believe it would be, God, I hate Newman projections. Like this, something like this, something akin to this. which your H's would be here, right? And your CH3 groups would be here. And you have two H's up here and here. The reason why your CH3 groups have to be kind of close to each other and on the right side is because they're both wedges, right? And knowing Newman projections, these two guys are not eclipsed, right? Because they're not right on top of each other, but they're close to each other. What word do we use when things are close to each other? Zoomies? You guys know? So they're not eclipsed. They're not anti. Starts with a G, and it's a French word.
Gauche.
Gauche.
Gauche, whatever you want to say. Yes. So they're close to each other, which means they are not as far away as possible. So it's not 180, right? And one's on the other side, so it's not that. And they're not right on top of each other, so it can't be that one. So one left is 60. And that's how you do this. Does that kind of make sense?
Yes.
Okay. If not, please tell me.
So each formation has a specific degree angle, right?
Yes. So if they're right on top of each other, where the methyl groups are literally blocking each other, that is a degree of 0, and that is a total clip, right? As you turn it slowly, right, they're not perfectly mirroring each other, but they're still interfering. That's gauche. And then you kind of go a little more, and then you kind of go, you turn it all the way. That's anti, goes back to gauche, and then total again. Technically, total, eclipse, gauche, anti, gauche, eclipse, total again. Yes. Yes. If one was a dash and was not, you would replace it with, whoops, I didn't do that, but sure. If one of these, like for example, is a dash, right? You go like this. Oops. Okay. Off to here, right? And then technically one's going here, one going here. CH3 is here, and the CH3 is here. So that would be 120, not 180. There you go. Yeah. Okay. Moving on to number 5. Yeah. Okay. So first things first, what's an enantiomer?
Mirror image.
It is a mirror image, right?
That's not superimposable.
That is not superimposed. Good. So your hands are mirror images, right? They're not superimposable, which means they're chiral, right? Enantiomers are mirror images that are superimposable, which basically means they have different RS, right? So if one molecule is R, the other one has to be S. So hypothetically, if one molecule is RR, the enantiomer is SS. Is making sense? No. If the molecule would be RS or SR, these are diastereomers, not enantiomers. Enantiomers have to be opposite. Diastereomers vary 1. Yep. Very, very confusing. Just knowing enantiomers are the opposite. Diastereomers are like in between. Okay. Do you guys understand how Fischer projections works? Yes or no? Mostly? You think?
No, they said that they're gonna go over it tomorrow.
He's not going over this? Oh my God, grubs. Okay.
Yeah, he posted a video and said that we should probably review it before lecture.
Okay. Let's go over it now. They are called the backbone because if you rip someone's spine out and lay it on the table, the ribs point up, right? So the molecules in left and right are technically wedges. The ones going up and down are dashes. So blacks are wedges, reds are dashes. Does it make sense? Zoomies.
Are there any just solid lines?
We need solid lines. No, not with this one.
Just only wedges and dashes. Okay.
We'll use it later. So with Fischer projections, we want to notice something. Oops. That's an H. H's are always what? Highest priority or lowest? Lowest. And do we want the lowest priority to be dashed or wedge?
Dashed.
You want the lowest priority to be dashed?
Yes.
Yes. Okay. Yes, you want to be dashed. So you want that one on top. Is the H right here? Yes or no? Is the H on top or is it a wedge? It's a wedge. It's a wedge here. 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 Right? Do you see it's all wedges? That means when we start assigning RS and SR, we have to do the exact opposite, the normal, because it's a wedge. Okay, so let's assign priority. This chiral molecule right here, which one's more important? BR, CH, C, or H?
BR.
Okay, 1. What's next? Going up or down?
Down.
Down. Okay. That guy right there, 1 to 2. That normally is S. It's anti-clockwise. It's sinister. Yes. Okay. So you always, 1 is always the heaviest. Second one is always the second heaviest, right? So where I put 2, that's a carbon. There's also a carbon here. So we just move on to the next guy, right? So carbon is bonded to a chlorine. This carbon is bonded to 3 hydrogen. So chlorine, carbon chlorine is much heavier than carbon chlorine. Erase. Okay. So what is this normally? S or R? S. But since I have my H as a wedge, sorry, H is a wedge, it has to be R. Okay. Does that make sense?
Yes.
Nope. That's when you rotate the molecule. We're not rotating. We're just looking at, yeah. Okay. Okay. For this chiral molecule, what's the highest priority?
Chlorine.
Chlorine. Good. Next, what's up? The one up or down?
CL.
The one up.
Good. So that would be counterclockwise, right? Which would be S normally, but now it's R. So now we have RR. So 1 is RR. Okay. What is an enantiomer? SS. Good. Okay. Same thing. 1, 2, going this way, clockwise, right? But yep, we are, but now it's S. Good. Here, I have 1, 2. That's normally what? R, but it becomes S. Good. Okay, 1, 2. That's going to be what? 1 to 2. Normally it becomes R. 1 to 2. Okay. 1, 2. Oh, other way. My bad. Which one? 2? Which one? Can show me. 1, 2, or 3. Okay, which one are you looking at? My bad. Okay. Technically, this guy's going this way, right? And that's an R. Okay. One, 2, 4, 3. That's normally A. Something in R, so it becomes A, S. So which one are exact opposites? 1 and 2. Does that make sense to you guys? Zoomies?
Got it.
Everyone else?
Can you show the direction of the, when you go to the second chiral carbon?
For which one?
Just for example, like the first one.
So I'm looking at this guy. Set priorities. 1, 2, 3, 4.
Okay, that makes sense. Thank you.
So that would be this way.
The answer is 3 and 4, right?
That's what the key says. I don't agree with the key. It doesn't make sense. I think he messed up because we assigned RS, RS. So the key says 3, 4. I'm saying 1, 2. I mean, you could try, show my work. Okay. Cade, Emily says hi. If you want to leave, Cade, you can. I'm going to upload this after I'm done.
Okay, thanks, Shane.
So even though it doesn't seem like it, Grubbs is immortal. He's immortal, not immortal. He can mess up. I think he messed up here. So I think 1 and 2 are enantiomers. 3 and 4 are stereoisomer because of the exact same configuration.
So the reason why it's enantiomers because they have opposite, so it's RR and then SS, so it has to be opposite, right?
Yes,
So what would 3 and 4 be?
they were stereoisomers because they have exact same.
Would they be identical?
No, they're not identical molecules. Because if we count like this, 1, 2, 3, 4, 5, 1, 2. Actually, it would be identical. Good job. It would be identical. 3 and 4 are identical.
Okay.
Yeah,
And
because
the
you can just flip it.
Yeah, these is flip.
reason why I think that, right, is because RS and RS, they're
Yeah.
also, okay. Thank you.
Yes, they're identical molecules. That's why they cannot be enantiomers. Okay. Now it's about heat of combustion. Okay. So what's that for? You guys laughing at? Okay. So anyone want to take a guess at this one? Cyclopentane would be the largest. Why?
It's the biggest
Yes, which one's the biggest?
cyclopentane
Why?
because it has 5 carbons.
Good. Has 5 carbons, right? Which means it can have like blow up more. Got it. Good. So what's the next one? Good. Heat of combustion. Heat combustion is different than ring strain. Make sense? Do not confuse those two. Okay. So ring strain. What is the smallest cyclostructure we can make? Propane, cyclopropane. The bond angle between these are very low, right? So they can't move around as much. So a lot of steric strain, a lot of torsional strains going on here, right? So what the molecules want to do is they want to be as far apart as each other. They want to be a straight line, pretty much, right? So what happens is as you increase in shape size, you get more stable until you reach the pinnacle of existence. Hexane. Hexane has no ring strain because all molecules are 109.5, which is ideal, which is almost a straight line basically. And then then it starts going back up until we reach I forget how to say 12, but the one with 12 rings, that's basically a multiple of cyclohexane. So it also has no ring strain. So, yep. Zoomies, we got that?
Yes.
Cool. Okay. We are looking at the same thing. Eyeball here or eyeball here, doesn't matter. Either way. Newman projection, go. Okay, that one's gonna go technically here. And that one's gonna go here. And which means it's gonna go here, goes here, and goes here. HCH3, HCH3, H. How far away are they? 60, 120, 180? Huh? They're 120 away. Does it make sense, Zoomies?
Why wouldn't it be 180?
Because they're not fully apart. For that to be true, it would have to be here and here. Because that's 180, straight line, right? Straight line went down. They are still within each other's vicinity. They're almost 180. If they were straight across like that, it would be, but they can't be with Newman projections. That makes some sense? Who asked the question? Do you understand it now or no?
Wait, why is the CH3 above the H?
Why is it above the, oh, because someone asked, why is it 180? 180 has to be a straight line. So I was just hypothetically showing in green, this would be an example of 180 away from each other. Or if it was here and here. Technically, that's not even true either. So it just has to be where the green one is. Green ones are. So that is the only example of 180, which is anti. What? Bryce, make sense?
Yes.
Okay. The other one who asked questions, make sense? I didn't see who asked. I'm gonna guess your question was answered and move on. Okay. It's asking for a dihedral angle. That means Newman projection. Okay. So which two has the methyl group? Either look from this way or this way, correct? Either way doesn't matter because one's a wedge, one's a dash, right? So line, one coming off the middle one has to be theoretically here, right? And the back one has to come off the other side, right? Okay. And you just fill anything else with H, theoretically speaking. So these methyl groups are not 180, they're not 60, They're not on top of each other. They're 120. Cool. Okay. Number 8 sucks. So we're gonna make a model kit. Model kit. You guys have not done this class yet, so it's easier to see this. Which one? So, your left side is going to the right side is going to
So funny, that's all I needed. That makes so much more sense now. Oops. It's like, dude.
Okay. A little molecule, guys. Let me show my screen. Spotlight for everyone. Okay. So here's the Fischer projection. I just added the OHs. Okay. Because the top and bottom are technically dashes, they go down. This guy go down, and this side goes down. Can you come help me hold this, guys? Just hold it. Just hold this. Okay, there we go. So these orange ones right here are going to be OH molecules. This blue one right here is an OH molecule as well. Okay. So when I draw this as line angle, and this is only true for going Fischer to line angle, these are going where? Out of the page or into the page? Out.
Yeah, okay.
Yeah, I see that? Kind of how the orange are coming at you, correct? Zoomies?
Yes.
Yeah,
Okay.
yeah.
Where's the blue going?
Blue's going away.
Away. Okay. This only happens with Fischer projection when you go from Fischer to line angle. And it's always the even ones. 1, 2, 3, 4. So since these are going out, they are going out. Okay. So which one does it show where carbon 2 and 4 have wedges, OHs, while carbon 3 has a dash? Zoomies? Which one
B?
shows a B? Yes, B is the correct answer. And that's it. I don't know. I had to use a model kit.
Oh,
I
that's great.
honestly do not know. I looked online to see, and every resource should use a model kit. So that's why I recommend having a model kit. You can probably ask for probably some weird way. I have to use a model kit. I can't visualize things in my head, so I have to use a model kit. That sucks. Okay. That makes sense, Sumis?
Yeah.
What, talking to grubs?
No, it was so irritating. Midterm crisis. And he like walked by and he just like stopped and just stared at me for a good like 5-10 seconds and didn't say a word and then just walked off. And I was like,
Because he's recognizing you.
yeah. And I was just sitting there, I was like, hi. And he just laughed.
Yep, which means he likes you. He likes you as a student, recognizes you. Okay,
Question.
answer.
Why
What's up?
OH dashed again? Like, because I don't have a model kit, so can you kind of explain it if you don't have one?
I honestly do not know. Every website I looked up, because I tried to find a way to do it without a model kit, I can't find a way. Ask Grubbs when he goes over the concept. I don't know how. The websites I looked up did not make any sense without a model kit. Unless you can visualize, since these guys are going down, right? These guys are going down. That means
Yeah.
this carbon is theoretically being bent and it's going down to the page. Because you can go up or down, which are wedges, right? Theoretically speaking, or axial. No. I'm just going axial going down instead of axial going up. But that's all I could think of. Okay, you're gonna have to ask Grubbs. Sorry, Madison.
Okay, thank you.
I'll look up and see if I can find anything tonight for tomorrow's study session. Okay. So, I don't know. You guys gotta figure it out. Don't come. Then come. Okay. Okay, then why not? Okay. So sorry about that. Somebody's talking. Okay. So how this works is with chair conformations, right? Chair conformations with cyclohexane are the most stable, right? So A and B are automatically more stable than B and C because B and C are considered the boat structures. They have more. They have a little bit more torsional strain to them, right? So they have a bit higher energy, right? Means they're less stable. So we want the least stable possible. So A and D are automatically out because they are chair conformations, and by definition, they are more stable than boats. Does that make sense to me?
Yes.
Okay. Up next, we have one going equatorial and one kind of going, even though it doesn't look like it, this is axial because a boat structure is a bit different than a line angle. Oh, sorry, a chair. So you want heavier molecules such as methane on a axial or equatorial? Equatorial, right? So which one is it not on equatorial? B. So B is the least stable out of all of them. Which one's the most stable?
D.
D is the most stable. Good job. In case he asks it vice versa. Okay. Oh, I hate this thing. Okay. You guys, I can't say it. Tell you guys after. Okay. You probably have a chart like this, somewhere in your notes, correct?
Yes.
Okay.
Yeah.
This chart is very important. What this says with chair conformations, when things are on 1 and 2, the cis conformation is when something's equatorial and axial. The trans is when they're the same, which is different when it's on an odd one, such as 1 and 5. Oh, sorry, 1 and 3 and 1 and 5. In which the cis is normal or the same and equatorial is opposite. The reason being is because 1-3 conformations are way more stable than anything else. So 1-3, 1-5, more stable. So we tend to do those ones as the most common one, which is you see is normally as cis or trans, you guys know from double bond type of stuff. So using this chart, right? Carbon 1, 2, 3, 4. So 1 and 4, right? This guy right here. One's going up, axial, equatorial.
Axial.
Axial. The methyl would be equatorial, which would make it cis or trans.
Cis.
This guy's cis. Okay. 1, 2, 3, 4. Or even the other way, it still equals 4. So same thing. The methyl group is axial, equatorial. Equatorial. The OH is
Equatorial.
equatorial, making it cis or trans.
Trans.
Trans. So when something's cis and trans, what are they? Are they identical? No, they're not
No.
identical. There is a relationship. I didn't sign IRS at all, right?
Is it an enantiomer? Oh, damn.
They're not. Nope. Because that's only with R and S. They're diastereomers. Because what? Diastereomers. Because they differ in 3D ordinal space. Okay.
Is it true that cis and trans are always going to be diastereomers at times?
Yes. They're always diastereomers. Always, 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 always. This was from the last exam.
Also cyclos and alkenes, right? Or it's alkanes.
It's A-N-E. It's alkane. Alkene. Alkane.
Okay.
And the reason we can do this is because it's cyclohexane. Cyclohexane can have cis and trans. It's weird. Okay. Because normally you need double bonds to have cis and trans conformation. But it's cyclohexane as a chair conformation. Chair conformation can allow for cis and trans. Cool. It's just as stable as a double bond. Erase, 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 erase. Number 11, I have no idea. I honestly have no idea. So we're gonna skip it. Because I don't know.
Triple R and triple S? What the?
Yep. We're adding these two molecule. I don't know how to do it. So we're not gonna do it.
Wait, what are we doing right now? Are we doing like a PLP review?
This is a practice exam.
Oh, this is one of the, oh, I see.
Racemic means it can be either dashed or wedged.
He said we don't know everything that's going to be on the practice exams.
Yes, I do not know this one. So that's why he's not gonna cover it. So we're not gonna do it. Most likely he's not gonna do it. So don't go over this one. That's why today I'm going to the practice exams. Tomorrow I'm going over the participation because those are more likely closer, but this is good to see harder versions of questions that could be asked. That make sense? Yes or no? The
Yes.
practice questions are gonna be like the hardest questions on the test. The practice questions, the participation question are gonna be like the easier ones. So we'll go over both. So 11, don't do. Okay. So enantiomers are what? Opposite. Good job. Huh? Huh? They're opposites. They're opposites and they are mirror images because of that. Okay, a priority. 1, 2. What is that? One, 2. So would those normally be enantiomers? Because they're opposite RS, right? No. Nope. There's a line of symmetry. They can fold on top of each other. Because they have separate RS conformations and there's a line of symmetry, they are Meso.
Can you go over the R and S again, please?
Yes. Okay. So here's your chiral center because it's bonded to 4 different molecules. One being an H, one being a CH2, one being a COH, and one being an OH. So the biggest molecule is O. So that takes first priority, right? Next is the CO bond, which is right here. Then it would be this guy. And then lastly, the H. And we go from 1 to 2. And it goes this way, which is what? Clockwise, correct? Which is R. Here we go. 1, 2, 3, 4. This is going anti-clockwise, which we call sinister. Because like a horror movie, if the clocks are going backwards in the haunted house, you guys would probably freak out. Okay. Yes, counterclockwise is stupid. If you want to know that, yes. Okay. Does that make sense, Madison? Because I believe you're the one that asked, right? RS?
Yeah.
Okay. Make sense? Okay. So since it has a line of symmetry, it is considered Meso. And Mesos are not enantiomers. So it's not it. Yes, they have to be opposites and have a line of symmetry. Not Meso. Yes. Okay. So 1. It can't be. Let's look at this one. Okay, yeah. What's wrong with this guy? Is this a chiral center? Why not? It has 4 bonds. Oh, sorry about that. Yeah, they're this party. Okay. It's got 2 CH2 bonds, right? So it's not bonded to 4 unique things. So not chiral. So not chiral means not enantiomers. There's no RS. No. Same thing with D, right? Not D. Those are going to be this RS as well. And they're not going to be mirror images because you can't cut them in half. So enantiomers. You can't cut them in half. There's no line of symmetry. Okay. Zoomies make sense?
Yeah, these
Cool.
questions are kind of confusing sometimes, like the way he words them. I
Yes, I
don't
know.
know.
It's Grubbs. He pulls them from like Purdue University and other graduate university organic chemistry classes and textbooks.
Can you go over BRS again, please?
Which one?
After the quotient, like why it's not line of symmetry and how to get the RS, because isn't it bonded to another CH2 or am I tripping?
Which one?
For 12,
For 12?
yeah.
So these two are chiral centers because they're bonded to four unique things: OH, H, CH2, and COH, right? And the same thing. So that means they're chiral. Same thing happens here. This guy right here is not chiral because it's bonded to two CH2s, two CH2s. So since it's not unique, it's not chiral, which means bad. Same thing happens here. Two CH2s, non-chiral. A is enantiomers because they are, well, it would be a normally enantiomer, but it's 1, 2, goes like that. There's 3, 4, which normally would be R. 1, 2, going this way, anticlockwise is S. But since you can cut this molecule half and it flips, there's a symmetry, right? Because you can fold it in half, it is considered a meso compound. Make sense, Madison?
Yeah, but what about B?
It is technically not, because it's chair conformation. Chair conformations have a hard time doing line of symmetry because they're chair. If you draw it out in a model kit, it doesn't work out. If you can't have a model kit, if you do this, technically 1, 2, right? They're both they are both equatorial, or is it both? Yeah, but equatorial. That means they are trans. So instead of having two wedges, it's having a wedge and a dash, and that can't fold in each other as evenly. Make sense, Madison?
Yeah, so for B, where would be the third priority located at if you were to do the RNFs?
Okay. 1,
Okay.
2, 3, 4. It's the CH2 group.
Oh, okay, I see. We're doing. Thank you.
Yep, of course. Anytime. I'll keep going until this cleaning staff kicks me out. Okay.
Okay, now this is something that Grubbs actually like didn't,
Over.
like he went over it a bit, but he said we were gonna finish it later.
Okay. Just know for optical activity, you have to have enantiomers. Optical activity has to be comparing enantiomer. Why? So there's an experiment in which when you shine light at something, right? The R and S can polarize light. Okay. It usually shows an experiment with like a light bulb having light hitting a compound, having polarized light, and then having like a wheel with a whole bunch of lines, and then a thing kind of go like this, which makes the light polar or polarized. So basically, optical activity can only happen with enantiomers because it's only you can polarize light. Enantiomers have different physical properties, and that's all this is trying to say. Optical activity is different for enantiomers. Diastereomers and stereoisomers will have similar physical property. Okay. So if you do the RS for these guys, Carlson here, 1, 2. What's that normally? RS, regular. But since we have an H as a wedge, it's, there we go, stupid. Ha, 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 ha. 1, 2, going backwards. So you are SR, which means we can be optically active. Here, 1, 2, clockwise. But since it's our hydrogen is a wedge, it's the exact opposite. So S 1, 2. That's one out there, which makes that normally R, SS. So, great. So, wait, what? His key's wrong. We're gonna skip this. His key's wrong. Okay, we're just gonna skip this. It's not gonna be that test. Optical activity usually is not heavily tested. Okay, what's going on? Okay, bye, Bruce. We're gonna kind of skip this. Hopefully he goes over it. If not, I'll make a video on it later. Because, well, it's 9:36. The computer shuts off at 10. I don't have time to go over all this stuff. Okay. This one's pretty easy. If optimal activity is negative, it is going to be L, a laboratory. Yes. Negative optimal activity is always going to be L. So positive, right? If this is positive instead, it'd be dextratory. No, D and L are not conformations. They are just how optically active they are. If they rotate to the left or the right, how polarized light. So these guys are wrong. Oh, sorry. These guys are wrong because there's no conformation of D and L. Sorry, no conformation of DL. And I'm not given a structure, right? So I know it's R and S, because R and S and optical spin are not, they're close to each other, but not the same thing. Okay, that makes some sense? The blue one, because it's negative, which is lavatory. Don't I do 15 because he doesn't do math. Grubbs hates math. So most likely that's not gonna be on the test. So 16. Okay. 16. Okay. These molecules, there's something special about them. What is it? One, two. Normally it's what? Regular. But since the fluorine, our number one, is dashed, it makes it 1, 2. That makes that S. Okay. 1, 2. Like that. Makes that what? Normally R, but now since the fluorine is dashed, it makes it S. What are the SR? Why? Which one? 1, 2. R makes it S. 1, 2. Do you see what I'm doing or no? Okay. So S. 1, 2. SS. 1, 2. SS. They're both SS. What's that mean, kid? Yes. Since the fluorine is a wedge, highest priority group, and the hydrogen is not wedge, we don't have to flip it. Okay. So they're not opposite, right? They are the same. They have the same conformational thing, right? So not structural isomers. They are identical. Make sense to me? It's just flipped. The molecules are just literally just flipped. So they have the same molecule, just flipped. Cool. Want to keep going and assume you guys are understanding. If not, say something. Okay. Dihedral, which means Newman projection. And we're the highest energy. So which is the highest energy? 0, 60, 120, 180. 0, because the molecules are right on top of each other. The CHs are right on top, right? They're eclipse, a total eclipse, which makes the answer 0. That is the highest energy. Zoomies, make sense?
Would you need Newman projection if it's just asking for the highest energy? Like, wouldn't that be 0 by default?
It would be, yes. But I do Newman because it's asking for a dihedral. Dihedral just basically means Newman projection.
Gotcha.
Is this helpful to you guys?
Very.
Yay. I'm glad it's helpful. Okay. What are the conformation of the following molecules? One, 2, 3, 4. What is? Yes. So normally it would go like this, 1 and 2, right? Which would be RS. Be R, but since our number 4 is wedge, it's the exact opposite. So it's S. So 1 is S, correct? We have 1, and we have 2, we have 3, and 4. Going backwards. Yes, it does. Remember, these guys right here are wedges. So number 4 is also wedge. So the exact opposite. So normally S is now R. So it's SR. Wait, what? Yeah, 18. What's going on? You're good now? Okay. Zoomies, you understand that one or no?
Wait, if hydrogen for 2 is wedged and it's going like that, wouldn't it be S or no?
So since this guy right here is wedge, we don't want hydrogen to be wedge because number 4 should never be wedged,
Right.
right? So if we do this, it normally would be S, but since our 4 is wedge, the lowest priority is wedge, it has to flip and become the opposite. Does that make sense or no?
No, because isn't bromine 1 and then the OCH3 2?
No.
OCH.
These are what's bonded to that our chiral compound. So we have 1 O, a C, and H. So which one's the heaviest? O, H, or C?
Oh.
Oh, that takes first priority, right? Next, we look at the 2 C's. This C right here is bonded to a bromine. Well, this guy's only bonded to another carbon. So this guy right here becomes 2 because it's the second heaviest. That makes sense, Madison?
Yeah, now that makes sense. Thank you.
Cool. Okay, 19. Boiling point. Okay. So, which one boils faster? No. Cyclostructures have higher boiling points. So cyclostructures have higher boiling points than their alkene counterparts. So it's always going to go propane, cyclopropane, butane, cyclobutane, pentane, cyclopentane, hexane, cyclohexane, and so on and so forth. Where cyclo always have higher boiling points than their counterparts. Does it make sense?
Yes.
Okay. So which one has the lowest boiling point? Which one's the smallest? Okay. Second lowest would be no. Triangle is the middle. It's got 3, right? This one has 4. 1, 2, 3, 4. Yes. Yes. It's just cyclo is better than its counterpart, right? Propane boils faster than cyclopropane. So there you go.
Wait, so the most branching is the highest, correct, boiling point?
Branching does affect it. Branching helps with boiling point, but there's no branching here, right? These are just structures themselves.
Or would it be considered more carbons then?
More
Sorry.
carbons.
Okay, and then the cyclo is it more dominant than the chain because, yeah.
It's considered more dominant because there's more CH2 bonds, which have more energy.
Oh, okay, thank you.
IUPAC names. Okay. So what's the first rule with IUPAC names? Alphabetical order, correct? Good. That is C. That is B. Is the alphabetical order? Sorry, alphabetical order, yes or no? No, it's not. So that's wrong. Cool. What takes more priority? Bromo or cyclo? Which one's heavier? Bromo, good. What takes more priority? Cyclo or methyl? Cyclo. So cyclo here is 6, methyl here is 5. That's not possible because it's not the right priority setting, right? Cyclo should come before methyl. Does it make sense or no?
Yes,
They numbered it wrong, yes. It is numbered wrong. Okay. Yes? Heaviest molecule. Okay. 2 cyclobutyl pentanol. 2 cyclobutyl propane. So that means only 1 molecule is coming off propane, and that is a cycle group. What number should it be instead of 2? It should be 1. So that's wrong. Yeah, here's propane, right? Yes. Okay. What is wrong with this guy right here? So what does tetra mean? 1, 2, 3, 4. That's correct, right? Okay. Heptane means what? 7 carbons, correct? All of these are bonded to one guy, correct? And then there's 7 other carbons. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Or they're technically not dead. Since you have a methyl group as number 1, right? That adds to the chain. There's technically would be 8 here if you do this. Does that make sense? Because it's the longest carbon chain. A methyl there would be added to the chain. Yes, we octane, not heptane. So you can't do that. That's why that one's wrong. So one left is the last one. So this one here is correct by default. Make sense, Sumis?
Yeah, so for B, since it's 2 bromo, 6 cyclo, since there's more, so since hexane is more, shouldn't it be switched to like 5 methylhexane and then 6 cyclopentyl since there's more carbon on the chain? Or
No, the issue with them, or what issue with B, is that this guy, first off, there's only 3 things there, right? Correct? Okay. Cyclopentanol weighs more than methyl. Does it make sense?
Oh, okay, yeah.
So it should be not that. It should have a higher priority than methyl. That's why.
Oh, okay.
Cool. Okay. Cool. 21. Which following statements is true? Diastereomers must be a pair of stereoisomers. Yes or no? Yes, that is good. Enantiomers have different properties. He messed the key up. I don't like this. Yeah, okay. Missed the key up. So diastereomers are stereoisomers, right? Because they have stereoisomers, they're different conformations. RS, SR, but not entirely different. So they're not enantiomers, so they're in between the two. So they are stereoisomers because they differ in like RS spin or like cis-trans. So that's why they're diastereomers. Yeah. Enantiomers do have different physical properties. I do not know why he says that one's false. Technically, that's true. Because he taught you guys about drugs, right? And how drugs that are enantiomers will be different. Yeah, he said that in class, correct? Or no? Okay. 21 has a lot of problems, so we're just going to skip it. But this one, most of them are true. This one's true. I know that for sure. Diastereomers had to have one or more, two or more chiral centers, right? Because RS, SR, in between has to be different. So di means two anyway. So 21 is messed up. So we're not going to do that. Need to make better quiz keys. Okay. CH3. I gotta draw the whole thing out. H, C, H, O, H, C, H, double bonded C, H, C, 2, 2, 2. Okay. How many chiral centers do I have? This is one, right? It's one to 4 different things, right? Okay. What else is there? It's really one. Is there? Zoomies, what do you think? Want to see one chiral center or do you see more?
There's just one.
There's just one?
See one.
Where? The ends? So it can't be those ones, right? And it can't be these two because they're double bonded, right? And you can't have a chiral center with double bonds. That's bad. Let me look at that. Okay. This one's also miskeyed because there's only one stereoisomer. I'm sorry, there's only one chiral center, correct? What? Yeah. This one's good. Yes. So there's only one. And the formula for stereoisomers is a number is equal to 2n. N is the number of chiral centers. So how many chiral centers do we have? 1. So the answer should be 2. Well, the key says 4. I don't see where you get another chiral center because there's no possible one. So he's been having a lot of issues with this key. So fun times. Erase. Okay. Which has the lowest energy? they're all chairs, right? So by definition, heavy group should be where? Axial or equatorial?
Equatorial.
So A's out has the highest energy, right? What's next? C's out. Then B and D. No, it's D. Reason being is 1,3 is less energy than 1,4. The reason being, equatorial, this guy is cis, this guy is trans. Trans is higher energy than cis. Since cis is a little higher energy. No, sorry, trans is. Sorry, trans is higher energy than cis. This double feedback is really annoying. Okay. Does that make sense? Yes or no?
Wait, so equatorial, isn't it highest energy?
What?
Is it equatorial highest energy?
No, equatorial is lowest. Axial is higher.
Okay.
The reason being, for A, the electron clouds for these two methyl groups causes steric strain. Them being far apart, less steric strain, so less energy. Because cyclohexane has no torsional strain, because it's as far apart as possible. There's no way to shift the molecule anywhere, so no torsional strain. So the only energy we can have is steric strain, or electron clouds being near each other. Sorry to interrupt you. Go.
No, you're okay. I was just asking, so axial is the least stable, but the highest, and then equatorial is most stable and lowest energy.
Yep.
Okay.
Yes. Higher energy you have, theoretically more often you're likely to explode. It's pretty much like the best way of thinking of things.
Can you explain the cis and trans with highest energy and lowest energy one more time?
I can. 1, 2, 1, 3, 1, 4. So having the same thing here and having opposites here makes this cis, and having opposites for evens makes it trans. So having molecules in different planes of existence adds some issues, because the molecule isn't technically even, so, and it can be a mirror image, so there is some chance of having enantiomers if possible, generally speaking. Being the same is less energy than having different parts. Does that make sense or no?
Yes, thank you.
Okay. Yay, 24. Okay. Let's go. 1, 2, 3, 4. 5, 6. That was your 6. Oh, someone said messages. Oh, never mind. Okay. Draw the molecule for this one. Make sure I got all correct. Yep. There you go. There's them all. Make sense? Zoomies?
Yep.
Cool. So there's 6 things. So 6 chiral centers, right? How many stereoisomers could there be? X equals 2 to the n equals 6. So it's 2 to the 6. A really big number, right? There you go. So lots. That's how you would do that one. Okay. Okay. Ring strain. So the higher up you go, less ring strain. So closer you are to cyclohexane, less ring strain. So which one is the farthest away from cyclohexane? Propane, butane, or pentane? Propane. So that one has the most. And then butane would be in the middle, this would be less. So 2, 3, 1. Does it make sense? Cool. So computer's still here and we have been kicked out. So go a little further. Cool, cool, cool. Okay. IUPAC names. IUPAC names. Which one? Which one is instantly wrong? We talked this one already. Exam 2. Oh, you guys want to? I'll stay. So I get kicked out. What do you want help with? Sure. Okay. Zoomies, do you want to keep going or do you want to stop?
Sure, let's go.
Let's go. Madison wants to go. Okay. This one's wrong. He's wrong because we already talked about that, right? Yes. A is wrong for the same reason. It should be alphabetical order. That's wrong. Right? Okay. Boom, boom. There you go. So this is pentanol. This is propane. I'm going to post a video tonight. Go home and post it tonight, which would technically be tomorrow because I won't be home until midnight. So yeah. Okay. Okay. So pentane is a bigger molecule, so it would be more important than propane. So D is wrong because this is bigger than that. This is bigger, so it take more priority. So pentanol is better than propane. Okay. So the answer has to be B. C is wrong too, because the T-butanol or isopropanol would add to the length of octane if you draw it out. So B is the right answer. Okay. We're going to do chiral carbons again. Oop, that's not there. No. Okay. Here's 1, here's 2, here's 3, here's 4, 5, 6. Oop, there's 5. Messed up where? Which one? Oh, this one here is bad. The bottom one right here is bad. So it's 5. 1, 2, 3, 4, 5. Why is 4, Kyle? It's bonded to an O, it's bonded to an H, bonded to a C. Yeah. So when I circle before, this one would not be chiral because there's 2 O's right here. So it can't be chiral. So it's the same. So the answer is C. So I got people in Zoom. Cool. Okay. So what's the relationship between these molecules? This says going up, this says going down. They are not wedge or dashed, they are lines. This guy right here is wedged, this guy here is wedge. So there is no wedges and dashes, right? So there's no 2, so it can't be the diastereomers, right? They're not different conformations. They're structural isomers. Does that make sense or no? Not really? Okay. Someone said not really. let's do this. Red, red, blue, blue. Red carbon bonded to a blue carbon. So here, here. So CH3, CH3. Red, oh, nope, that's not red. Red, blue. This one has a carbon here. This has a carbon here. So they have the same amount of carbons and hydrogens, right? It's just how they are arranged is different. So they are structural isomers because they are the same chemical formula, just rearranged differently.
I see it now. Thank you.
Of course. Okay. We're not doing number 4 because it sucks. 5. Okay. We have a Newman projection, right? So we have to draw a Newman projection out as a line angle. So boom, boom. Yep, CL is going to be wedged, right? Well, H is going, sorry, CL is be dashed, H is be wedged, and then you have a random methyl group coming out. On the back carbon, we also have a dashed CH3, right? A normal Cl, and also a wedged hydrogen. Now it's not drawn accurately, but it should work. Technically, if you want to make it better, that's going down, this would go up, so it would affect it. Hate Newman projections. 1, 2, 3, 4. 1 to 2 would normally be what? S. But since our hydrogen's wedge, it's R. Okay. 1, 2 would normally be R, but since our hydrogen's wedged, it's S. Okay. This one's already lined angle for us, so you can already do nice. 1, 2, 3, 4. So we would do this way, right? Yeah, it would be S. That would be R. Right? It's going counterclockwise. So we R. No, it would, because it's going backwards already. Oh no, we wouldn't. We would avoid the 4 as much as possible. Right? So we go this way actually, which is R, but we make it S. We avoid 4. That's right. That's the stupid rule. Okay. 1, 2, 4, 3. Go this way. So it would be S. We make it R. Because we try avoiding 4. Try avoiding 4. Okay. These would be then what? RS, SR. They're exact opposite, right? No. They're enantiomers. Because they are exact opposites, right? RS, SR. That's if they're RR. If they're the same one, the exact opposite would be the exact opposite one. For this, because they are RS, the exact opposite would be SR. Diastereomers would be example would be RRR or SS. that would be diastereomers. That make sense? Zumi?
Makes sense.
You sound tired.
Yeah.
It's only 10:11. Let's go. Most stable. B and C are automatically out because they're boats. Boats are not stable. So A and D. Which one has the methyl on the equatorial? D. D is stable. Move it on. Okay. One, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So which one has a higher boiling point? More carbons makes you higher boiling point, right? Okay. So which one? 2 or 3? Being cyclo, having a ring, makes you have a higher boiling point than your counterpart. So 2, 2, 3, then 1. So it would be D. Branching there really doesn't do anything because it's carbon chain. Carbon chain comes first, then branching can affect things. But more carbons makes you a bigger molecule, which means you take longer to boil. You cook an adult person cooks slower than a baby. There we go. Okay. 1, 2, 3. 1, 2, 3, 4. Wait, he messed this one up. Whoa, nope, backwards. Numbering's backwards. 1, 2, 3, 4. For some reason, the key says E. I don't know how. I don't see them as structures or isomers at all, because the heavy molecule is both equatorial. So a ring flip won't do anything. So that makes no sense. The key says this. I don't know how it's that. This guy right here is trans. This guy right here is cis. So I thought they had to be diastereomer. But the key says E, but I would say D. I would argue D. I would fight them. Okay. Okay. This is part of the last exam because computers didn't shut off soon. I got a notification. Okay. A symmetric relationship between A and B. Did he just? That makes no sense. Okay. One, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 1, 2, 3, 4. Okay. They are not the same structure, right? They are rearranged in a different way. So they are structural isomers. So there we go. We've done this one before, right? how did he put A? That's not true. The answer for this one is D. He said 0 is most stable. I don't see how. Yeah, the answer should be D. He keyed A. I don't know how. Having 0 would mean highest energy, least stable.
How
So
would it be?
what?
Can you explain 10, please?
Yes. So dihedral, Newman projection. So this, 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 this. Both CH3s come off each other, right? Yeah, both CH3s come off each other. So they go right next to each other. Oh, I see what you did. 10, say. Oh. And then we have H here, H here, H here, H here. Right? So we are in what angle? Total eclipse, right? It is 0, but for some reason he says most stable. That wording right there is very bad. If that was not there, that would be correct. This would be 0, right? But total eclipse is not stable at all. Is the highest energy Newman projection. So it's not stable, but it is the angle given. That makes sense, Madison?
Yeah, I'm just more confused on like how you arrange it on the Newman.
Okay, be quiet. Someone said shut up. It's all good. Okay.
Sorry, though.
It's all good. Okay. If you are wedges, you come off to the right. So both are wedges, so they both come off to the right, right? So they're gonna be right on top of each other. So that's why the angle is 0, because of the total eclipse. If you come off to the left, you are wedged. You're wedged. Like off or like somewhere around here. It's because it's cyclopropane. Propane can't really do that. Because if you think about it, they are literally blocking each other. If your eyeball would be right here, you could not see, we could see the other one because they are literally blocking each other. Vice versa goes here too. They block each other, which makes it total eclipse.
So if they were dashed, what would that then be like?
Same thing.
Oh, okay.
It would just be on the other side. Instead of be on the right side, it'd be on the left side, but they would still be eclipsing each other.
Okay, thank you.
11, we're not gonna, 11 we could do. It's positive, which makes it dextratory. So the answer is A. Lavatory is negative, so it's wrong. And you can't have conformation of D or L, and they are opposite of RS. They're not the same thing, they're different. So he's the answer. Erase. Okay. Heat combustion. Which one's the biggest? So 3 is first, right? Wrong, 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 wrong. So E and F. Which one's the second biggest? 2. F. That's it. Pretty easy. These things right here and answers the same physical properties. That is the same mixtures. So the answer is C. So there we go. Okay. 14.
Wait, wouldn't diastereomers have more than two
They
chiral?
should. I don't know why he's saying no. And a lot of issues have been with the key already, so I would have an issue with that. So yeah, that's a problem. I agree.
So would it be like 2 and 3 then?
2 and 3, 2 and 3. I would say 2 and 3, 2 and 3. Yes, I would say D would be. Yes, but the key says C. So he's saying this. I'm saying this. So I will come clarify this tomorrow, my next video. But I'm just trying to go through this really quickly because the staff keeps walking by and they keep giving me eye. So try to be as quick as possible. Sorry, I do apologize.
That's thank you.
Okay. So chair confirmation. The best one would be in what? All equatorial axial. Equatorial, right? Which would be D. D is all equatorial. So D's the right answer. 15, I don't know how to do. I'm going to skip it. 16, I'm going to skip because it's not going to test. Cool. So this guy and this guy, how are they related to each other? The answer is staggered. Because if you look at this molecule, right, like an eyeball right here, and you're looking at this guy, this would be your front carbon, this would be your second carbon, right? And it would be an ethyl group coming off, right? And between carbon 1 and this guy right here, like this whole guy right here, they would be staggered. It would not be cis or trans, because you can't have cis or trans, because cis and trans can only be things coming off the cyclohexane. So these are wrong. And they're not eclipse, because eclipse can only be things coming off the Newman projection, and they can be Gauche. So the only thing that could be is staggered. Okay. Cyclohexane has the lowest ring strain, so that'll be the last one. So here and here. So between those two. Next up is 1, 2, 3, 4, 5, 6, 7, 8. 8 is closer to 6 than 4. So it would be B. '19 is the exact same problem we already did. So I'm going to skip it because it's the exact same problem. Okay. So dihedral methyl groups, right? So what is the lowest possible angle we could have for Newman projections? 0, 180. Which one? Which is the lowest energy? 180. 180 is anti, which is the lowest energy. So it's the lowest energy possible. Okay. This guy and this guy are in a straight line. What's an angle of a straight line? And 180 is the lowest possible, which is anti. There you go. That's why 21 is anti, because it's technically a straight line. Sorry, what's up?
Can you explain that one a little bit better? I'm kind of confused.
Which one? 20 or 21?
21.
Okay. So if you draw it like this, right? Carbon, this carbon and this carbon are in a straight line from each other, correct? Do you see that or no?
In a way.
In a way,
It's straight how you wrote it out, or?
yes. That is how. If you don't like that, looking at it this way, right?
Uh-huh.
They look like they're a straight line. If you look at it straight on, looks like a snake almost, right?
Right.
So it's anti. Because it's a straight line. If you look at it from the front.
Okay, if they were to move those arrows differently, would it still be anti?
Yes.
Oh, okay, I see where you're coming from now. Okay. Thank you.
Oh, let me have a birthday party. I want to join. Okay. Gauche. Torsional angle between two functional groups are gauche to each other. So 30 is wrong, right? Gauche have, and 90 is wrong, right? So gauche are always 60. That's just how, that's the definition goes. Gauche are 60. Going up, going out like this. The angle here is 60. That's the definition of gauche. So if you hear gauche, the angle is 60. So there you go. Okay, 23 is much easier. So bromine is axial or equatorial? Axial. Chlorine is equatorial. Ring flip it. You would have bromine as equatorial. Yes. So, let's see. There you go. This would be cool. Yeah. For some reason, he says B. I don't see it. I see C. Whoops. Okay. Meso compound. The answer is B. It's a line of symmetry. C would be 2, but the issue being these are not chiral, right? Where I circled would not be chiral because it's CH2, 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 CH2 could not be chiral. So then one with opposites and the mirror images is B. That makes sense? Okay. Lastly is 25. Okay. We have this guy. We have this guy. No, yeah. That guy's right there. This guy and this guy. 1, 2, 3, 4. There is more. I'm missing some. Where? Oh, that's all I see. I only see 4. I don't see any more. Chiral carbons. You guys see any more? I don't see any more chiral centers. Do you?
I only see 4.
Mackenzie? C4 as well? Okay. X equals 2N. And what's that? Is C. He says D, which means there are 6 more, 2 more. I don't see it. So I'm going to say C. And C messed up. But the computer's ready to shut down. Before I go, does anybody have any questions for me?
Are you doing this Zoom tomorrow at the same time?
I do not know. Maybe.
How do you get these like announcements? I got it from my friend, but
Email me at shane.dunn@my.gcu.edu.
okay.
Email me so I can email you.
Okay, thank you.
Yep. Okay, the computer literally just shut off. Cool. Okay, see you guys. Bye.
Thank you.
Of course. Okay. Stop sharing. Leave. Oh. Go away.